So last time we talked about parallelism. I'm not going to spend a whole lot of time reviewing that, or really any. Just we have the 4 different types, data and task as far as what we're trying to do, and then shared memory and message passing as far as how we do it, how it's in the data across. Then we talk about architecture and how the GPU is really pretty much just a miniaturized and at the same time larger version of the CPU. It's the same basic outline, but with a lot of processors instead of just one really powerful one. That's basically all there is to last week. And then we got to this brief look at CUDA syntax. And that's about it. Syntax we're going to dive into a lot more this time around. But were there any questions about last week?
I'm good for last week.
Okay. Okay.
I'm good too.
Okay. Good deal. In that case, we will go into this week, and I'll make this big for you here. There we go. Okay. So this is kind of where we left off last week. It looks slightly different just because of aesthetics, but nothing else. Do you have a question, Evelyn?
Like, have you started recording the meeting?
Yes.
Okay. Just checking.
I appreciate it. I appreciate it. Yeah. Okay. So we're starting kind of where we were last week. This is the same kernel that we ended off with. And all we're doing is just taking 2 arrays and adding them together, saving it in a 3rd array. So we got A, B, and C. We add the elements of A together into C. What we didn't look at was how to actually use that kernel. We just kind of had that definition. So what do we do? Well, that's exactly what we've got here. So this will be inside your main function. You have to call this from the host side, the main program. So just inside your normal main function, you would use a statement like this. And it's kind of a funny notation. It's called triple bracket notation, and we're going to break it down on the next slide here. So you can see we've got 4 different parts. The first is just the name of the kernel you want to use, just like a function. We're going to skip that middle bit for just a second. And then the last bit is just the parameters. So those 2 parts you're used to is just like a function. Function name, function parameters, same thing. The part in the middle is called triple bracket notation. And that you don't really need to know that. It's just called that because it's got 3 brackets on either side. What's inside there is specifying the number of tasks we want to use at one time. And it's, of course, in 2 different numbers, as you can see. We're actually going to start with this 32 here on the right. This is the kind of the smaller dimension, as I like to think, but that'll make sense in a minute. The 32 there, that second number, represents the number of threads per block we want to run. And essentially what this is saying is, I want to run this many individual processors on this kernel. So if I have a 32 there, then it's saying I want to run this thing on 32 different processors. So this could handle adding values from arrays that are 32 elements long. If we needed to do 64, then we could put a 64 here, or we could run 32 one twice, whatever it is. This is just telling you how many elements it's going to handle at one time. And another part of that is, this is actually how many individual cores, like we looked at in the architecture, the individual cores that you're allocating to run a kernel. Last note there, you can technically have any number for this threads per block value, the second value. But there's a minimum of 32 threads they're going to be launched every time. No matter what number you put there, there's going to be at least 32. And it's actually going to be launched in multiples of 32. So if you were to put 35, for example, it's actually going to launch 64 threads. Now, that doesn't stop you as the programmer from launching any number you want to, but you're essentially wasting those other cores that aren't being used. So if I'm launching 35 cores, well, then the other 29 that I'm not using out of that second batch are just sitting idle, not doing anything, and they can't be used for anything else either. So that's something to be aware of. So that's threads. Threads are organized into what's called blocks, and blocks are basically running at the same time. I say basically because there's some intricacies you can get into later, but for all intents and purposes, it's running at the same time. So if you put 32 threads per block, then you know those 32 threads are all going to complete together, or 64, or 256. This number can be relatively large. It's going to depend on your hardware, but generally about 1,000 threads, 1,024 threads is the max. So you can use quite a few. And those are all going to run, again, roughly the same time. On the other hand, this other number, this 1, represents the number of blocks we want to run. So a block is a group of threads, and the size of the block is this other number we've been talking about. So if we had a really big problem we wanted to solve, and 1,024 threads wasn't enough, then we can say, okay, I want 2 blocks of 1,024 threads, or 8 blocks of 1,024 threads. This number is essentially limitless because it doesn't have to run in the GPU at one time. They'll actually run at different times. You don't really have a reliable way to know when it will run, when it will be scheduled. You just know that it will be done at some point, but there's no guarantees to when it will run, and blocks aren't guaranteed to run beside each other. So you got to be careful of that too. That can cause some synchronization issues that we'll look at a little further down the line. So you got a number of blocks and a number of threads, and if you multiply these together, that's the total number of threads or cores that's assigned to a kernel. So you can get these giant numbers of threads assigned to something, and that's why GPUs are really great for accelerating things, because you can have a large number of tasks being done at the same time, whereas a CPU would have to do all those things manually, one after the other. Now we're going to go in a completely different direction. So before I do that, did all of that make sense, or was it all complete nonsense?
Makes sense. I have a question though.
Okay.
Is there a case where like there's an advantage to doing like 2 blocks of 32 rather than like 1 block of 64?
Yes, to a degree. That small of a scale, generally no.
I just meant like in general, like splitting up the same amount of threads in different blocks.
Yes. So when you get to things like, you get to kind of more advanced methods, there are benefits to being able to have multiple blocks do something at the same time. Versus if you use bigger blocks, you may not be able to schedule as many. So let's think about if you were going to do different tasks. If I had 8 blocks for a task that are pretty small, and 8 blocks for another task that are pretty small, I can kind of intermingle them, and they can fit on the GPU together. Whereas if I had 4 that are larger, I may only be able to fit maybe 2 at a time, and so I may just be doing less progress on both, even though I'm still essentially using the same amount of work overall. That may have made things more confusing, I don't know. And actually, there's one other thing I was thinking of. I don't recall. But does that help answer the question at all?
Yeah, I think I got it.
Okay. So yeah, the short answer is yes. There can be benefits to that. There's also benefits to using large blocks as well. blocks actually share memory. So they can share a memory pool that just that block can access. And if you work across multiple blocks, they don't have that benefit. So you have to do more communication if you're going to use multiple blocks for some things. That's another thing to think about. So, both good questions. Fortunately, the answers are probably a little past where we are, but that's okay. Okay. So no more questions on that part. I'm going to go with no. Now we're going to step back and look at something that has nothing to do with GPUs, because it's kind of a foundation that we need to go back and build because you guys don't really know C, or at least that's my impression. So straight out of C, we're going to look at pointers. So what is a pointer? It's just a block of memory. That's all it is. You don't really know it yet, but you're used to operating on those. Do you have a question?
Yeah, I'm asking, does CUDA only work with C? Can it work with C++? Can a person use CUDA and C++?
It can, but this is, well, it's semi-opinionated, semi just kind of what I've seen. It
Okay.
seems to be based in C more so than anything else. So that's
Oh.
what I'm going to teach you guys.
Thank you.
Yeah. But yes, you are correct that a C++ variant does exist. I just don't know if it's going to be the best way to utilize it. To be honest, I haven't used it as much, so I can't say for sure.
Okay.
Yeah, but even in C++, you need to know what pointers are. So you can use CUDA C++, but this is still going to be something you need to know. Okay, so pointer is just a block of memory. You've been using them, even though you may not realize it, and that's just generally because the languages you may have been using, like Java or Python or whatever else, does have to use these. It just kind of does it for you. You don't necessarily see what's happening. So pointer is just a block of memory, and if you were to print the variable that is a pointer, it's just going to give you a memory address. That's all it is. It's just a memory address. I also have this point about passing by reference. If you know what that is, then that's good. You know that basically it can allow you to modify things as far as parameter passing. If you don't understand what passing by reference is, that's okay. I'll kind of explain that a little bit later. Okay, so here's kind of a little bit more visual example of what exactly is going on when you use a pointer. We got the same, in this case, this is the CPU version of that vector add function. And we've got three pointers here. Like I said before, each one of these is just an address. I've actually used, I've used, what is this, 48-bit addressing for this. But, so it's not a real address, but that doesn't matter. The concept is A in the program, A just means this address. That's all this tells us. And B represents this address, and C represents this address. And then if we were to get the value at A, then it just says, oh, okay, I've got this address, so you want me to go here and get this value. Same thing with the other pointers, any pointer. The other thing that we can do here, and when we can use that address to get a value, is we can actually use the same array indexing format that you're used to. But under the hood, what that's doing is it's saying, okay, C is a pointer. I want to get element 3, so I'm going to add 3 to the address. It gives me this new address, and oh, hey, that's the element you want. And it gives you that element in return. Have I broken anybody's mind with this? Okay. Because I know pointers can be a sticking point for a lot of people. All right, cool. Oh,
So
go ahead.
how did the, okay, C at 3 is like I. 3 is the value of I, right?
Yeah. So you can think through if this was in whatever it is,
Uh-huh.
you would have iteration 3 and then yes, yeah. But you can also, of course, just use
I
3
think
there.
I see, but I don't get how the address is becoming 35. The 35 at the end of the bit, like how it's adding up. Oh,
So these are just random. When you allocate a pointer,
uh-huh.
generally they're not right next to each other. So this wouldn't normally be 0 and then 0, 4 and 0, 8
Mhm.
because the compiler and the language, the computer, I guess would be the better way, will naturally try to leave space for something. Because if you had these right next to each other, and then suddenly you needed A to be larger, then you got to move a whole bunch of other stuff just to make A larger. So leaving space is a little more efficient. So yeah, these are just addresses. They don't actually mathematically add up in any way.
Thank you. I agree.
Okay. Good deal. All right. Well, if we don't have anything else, I'm going to go ahead and move on. All right, so we covered what they are. Why do they exist? Why do we choose to deal with these things? Because they can be kind of pesky. Well, the answer, like I kind of already said, was they have to exist. But the higher level stuff that you're probably used to just hides the pointers for you. And I said it has to exist in order for a persistent variable to exist. What that means, let's think of an example like, let's say we have a function that just sums an array, right? You can think about it in Java or whatever language you want to. It takes in an array, it produces a sum. So how you're going to do that is have a sum value, just an integer, and then you're going to add to that all of the elements in the array, and then return sum at the end. That sum value that's returned is just an integer. There's nothing associated with it. There's nothing else. You're not getting the memory address. You're not getting anything more complex than just a number. So if you wanted to try and change the value of that sum variable, you can't because the variable itself just doesn't exist anymore. It goes away after the function executes. Persistent variables are the opposite of that, where you have something like an array or an object in a language like Java, and you can declare it in the function, but you can actually hand it to something and use it outside of where it's declared. So if you had you can have a function, make an array, for example, return it, and then whatever outside program you want can actually use that variable. It exists. It continues to persist and exist. So there's that idea of persistent versus local. So anytime we want something to stick around, we have to allocate memory for it. And that requires the use of pointers, whether we see them or not. Okay. And again, the whole allocate, so we're going to look at allocation here. The process behind why we have them and what they are is, again, they are addresses. We have to have an address as sort of a handle to use something again. Otherwise, we can just take its value and pass that somewhere else, like we did with the local variable. Okay. So what can we do with them? Or in other words, how do you use them? First off, you can make one. That's called allocation. You ask the OS, say, hey, give me a piece of memory. Here's how big I need it in bytes. And it gives an amount of memory back to you. It gives you an address back that says, okay, I made your memory allocation. Here it is. This is where it's at. That's what's happening here. Oops. I keep doing that by accident. That's what's happening here. Is we declare the pointer type. So this int star means integer pointer. Pointer is just the name, of course. And then we're setting it equal to the address we get back from malloc. Malloc just stands for memory allocation. And we tell malloc the number of bytes we want. Now that would be kind of difficult if we didn't have this kind of handy size of function. If you had to tell it, okay, I need exactly this many bytes, it might get kind of tedious, but luckily we have size of, and what it does is it just takes any data type. And this can be complex data types, or like if you make your own data type, which is doable in C, it will find the size of that in bytes, and then you just multiply that times the number that you want. So size of data type times number of elements. It looks kind of scary, but it's really not. And then the last thing we do, kind of in the middle here, is cast it back to an integer pointer, because this is a generic address, I guess I should say. This tells it it's actually for integers, so if I index it, I'm using elements that are of integer size. It just allows it to process it as an integer pointer versus a generic one. All right, I'll stop for questions there. Anything as far as why pointers exist, kind of what their purpose is, or allocation?
So if you make a pointer, can that be accessed outside of like the scope of where you made it?
Yes.
Okay.
Yeah, that's the whole, that's the exact thing with persistent variables. The pointer is the, in the most basic form, persistent variable. Yeah, so that's exactly it. Yep, okay.
I have one. So what if I don't put that make int? What type would it return? A generic pointer? What would it be?
I'm sorry, I couldn't catch most of that, Grace.
If I don't put that middle part, the int pointer, what would it return? Like, what would the pointer be? Can it be any? When you say generic,
Okay, I still am having trouble understanding you, but I think I got what you're saying. Are you talking about malloc? Oh, I did it again. You're talking about malloc and then whether it can be of different types?
I'm talking about the int before the malloc.
Okay, so this int pointer just needs
Yes.
to match whatever type you want to put here. So I could have an array of characters or chars, and we could put char star here. This just makes, let me put it this different way. Malloc just gets memory, right? Untyped, designated memory. And then the cast here tells us what kind of memory we want it to be. We want it to be for integer memory. We want it to be for double memory. We want it to be for character memory. That's what this is doing. And you would just need it to be the same type as whatever you declare the pointer as.
Okay.
Did that answer the question?
I did. Thank you.
Okay. All right, good deal. Okay. Okay. We will move on then. This one's easy. We already saw indexing. So that's just getting and setting an element inside a pointer. This is just like an array. It doesn't say it here. Actually, let's see here. Is it? I thought I put something else here, but I guess I did. Okay. Well, anyway, oh, there it is. Okay, good. I am smart as far as I thought it was. So anyway, indexing. You can use it just like an array to get an element inside a pointer. This can get weird if you don't use it like an array. So if you had some sort of complex data structure and you were to try this, there's no telling what it would do. But in general, if you're setting it up to use it like an array, you can do this. So for this integer pointer, this would be totally valid. Okay. Next thing is dereferencing. So this is essentially the same thing as indexing. And you'll notice the star again here. This is the dereference operator. All this says is, I've got this address. I want you to do something to the value that is at that address. So this is the base address here. This will be equivalent to pointer 0. You can see in my comment. This is the same as setting pointer 0 equal to 2. You can also do integer arithmetic on addresses. So you can move forward a certain number of addresses and change that, what that address holds. So again, we're adding 2 to the address. So this is the same as pointer index 2, element 2. And then finally, deallocation, returning memory to the OS. And that's just done by using its call to free. And all you do is give it the pointer. It's as simple as that. To use pointers, these outside to malloc and free are required every time. You're not going to get the memory unless you call malloc. And your program is basically broken unless you call free. It may compile and it may run, but you've actually got what's called a memory leak happening. So if you've heard of that before, that's where it comes from. You just have memory that is still being taken up by the program, even potentially after it completes. So you just have all this unused memory that you're done with that hasn't actually been returned to the computer. So that's the 4 basic operations there. Questions on any of those? Okay. All right. So we covered the main way that you're going to get pointers, which is explicit allocations, but they can come from 2 other places. Like Garrett's question earlier, they can come from function return values. So you just create one in a function, you can return it, do stuff with it later, and the important note there is you have to free it later as well. So it doesn't just get free just because it came from a function. You've got to free it later on too. And finally, for this slide, the reference operator. So what the reference operator does is it allows you to get the address of something you've already declared. So in this example, I've got this integer val, and now I want to make a pointer or get the address of val. So I put the ampersand, that's the reference operator, in front of val, and now this is a pointer type. And then I can dereference it, the pointer, and set that to 2. If I print val now, it's going to print 2 because I've modified the value of val. Obviously, in this example, it's kind of pointless because you can just call set val equal to 2 directly. But when you look at things like functions and parameters, this becomes really useful because you can pass in an integer. And normally with functions, when you pass in an integer parameter, it's just going to copy the number that's there. It's not going to do anything with the variable itself. So if you set the parameters, it's not going to change the original variable. If you use this reference operator and pass it that way, you will be able to modify that value in a separate function. It'll pass it by reference instead of passing by value. If you don't fully understand that concept, that's okay. It's just to kind of come full circle on what this reference operator is.
Riley?
Yep.
Which one is explicit allocation?
Are you asking which one holds the memory address?
Like explicit allocation here, where do they come from? Like where do the pointers come from? Then we have explicit allocations. So here, like this is value, this is pointer. Like
okay. I think I see. In this example, this there is no explicit allocation. That's
Okay.
actually this right here. This is an explicit allocation.
Obviously. Oh, I see.
Yeah. Yeah, that's the explicit allocation right here.
Okay, thank you.
No problem.
Then do we have function return values?
No, because I didn't define a function here. All this is
Okay.
saying is you can define a function that returns an integer pointer type, just like it returns an integer or string or whatever it is. You can define
Okay.
functions that return pointers.
Okay, thank you.
Okay. So having built that up, let's talk a little bit about GPU pointers. They're essentially the same. You just have some separate functions. So you can see here, we still use the same type declaration. Oops, I am so bad about clicking the mouse, I should. Anyway, we use the same type declaration, just integer star in this case for an integer pointer. But to, I just realized I made a mistake here. Oh, actually, tell you what, we'll go behind the curtain here and I'll edit it as we go on. So what I should have done is this. So you got the integer type. Instead of malloc, we've just got CUDA malloc. It's essentially the same thing. And it takes the same parameters almost. If you recall, I'll put this back in slideshow mode now. Well, in a second. If you recall, malloc just took this, right? So if we wanted 4 integers, we just need the size of int times 4. CUDA malloc also takes this first parameter, GPU pointer. And this is actually the reference to GPU pointer. There's a reason it does this. There we go. Hop back to full screen here. There's a reason it needs that reference variable, and that's because it's going to set this pointer that we declared to an address that is on the GPU. So it's still essentially the same as malloc, but it has to be CUDA malloc because only CUDA malloc can give us a GPU memory address as opposed to a CPU memory address. That's kind of what these points here are saying. GPU memory is entirely separate, and if we use the normal functions, we would get host memory addresses. The GPU can't access host memory, and host can't access GPU memory. So if we tried to use a null pointer with a kernel function, it would just break. Our program would fault and nothing would happen aside from the error. So notice here I put call GPU kernel. This is just do all of your stuff with that pointer, and then when you want to free it, it's just very simple, very similar to the other free, except it's CUDA free and GPU pointer. So GPU pointers essentially the same, they just happen to be on GPU memory. And if we want to move data from CPU to GPU or the opposite, then we have to explicitly copy it. So here's a mini example for us. And I forgot the size again here, but I'll add it later. We got a host pointer. In this case, we're allocating it as an array. So we've kind of hidden the pointer step here. But it is still a pointer, don't make no mistake. Then we've got our device pointer using what we just saw. And now we're going to copy from host pointer to device pointer for integers. And then this last bit is a, I forget the word for it. But anyway, this last bit is a dedicated CUDA keyword that says we're going to go from the host to the device. More on that in just a second. So break that down again. The first parameter here is our destination, which is why we put device here, because we want to copy from host to device. Second is the source pointer. Third is number of bytes to transfer, so 4 integers worth of bytes. And then last is the type of transfer. And you can see the 3 keywords that you can use here: host to device, device to host, and then device to device. You don't need to worry about this last one. It's for multi-GPU machines. And that is basically it for memcopy. I would need to add the size of the allocation to this CUDA-malloc. So you can just ignore that for now. Any questions? Okay, I'll move on. All right. So we're about to transition over to Visual Studio and a couple other things where we'll look at a fully put together GPU program. But before we do that, I just want to run through all the elements that every CUDA program is going to have. So first is a kernel. You got to have a kernel to run on the GPU because that's the only things that run on GPUs is kernels. Memory initialization. Malloc. You may need malloc if you're going to use host stuff. Definitely have to have CUDA-malloc for CUDA variables. Kernel launch using that notation that we looked at before. Memory transfer if needed. So if you're going to send things back and forth. And then memory deallocation. Just like with host pointers, you have to deallocate your CUDA pointers. Otherwise, you have, well, an ill-formed program is the best way to put it. And that is pretty much it. Any questions about the presentation? If not, we will move on to getting into some code. Small code, it's not anything complicated. Okay. I'm going to stop sharing briefly, and then I'll share again with you in just a second. Okay. I don't know why that's there. There we go. All right. Everybody see VS Code and the command prompt?
Yep.
Okay, good. All right. So let's go over what I've written here first, and then I'll show you guys running it again just to show you how to log in and run a file one more time. So quick note first, this C standard IO is because we're running a CUDA file, it needs to know where I'm getting printf from. So that's where printf is defined for CUDA, is C standard IO. That's the only thing it does. Okay, so kernel, we've seen this kernel a few times now. But just to recap, it's using the index-based thread to add together elements from 2 vectors into a third one. Simple enough. Oh, then we come into main. In C, of course, I think you guys know this, but just in case you don't, in C, main is where the program will always start. So you start in main, and then everything executes from here. The size is just a handy thing I put so that I can replace all of these uses of what would be a number with a variable that I can change. This is just the size of the arrays that I'm making. It's arbitrary. It could be whatever you want it to be. Okay. Here we're allocating 3 different arrays, and then we fill array A and B with, in this case, 1 through 16. It would be 1 through size. So we're just filling it with consecutive numbers. It's going to say, oh, this is a common convention, this H underscore. This means host, and then D underscore means device. Because it can destroy your program, it basically stops all progress. If you get your pointer swapped and try to give host pointer to the device or opposite, generally it's preferable to label them very clearly. That way you can see where you're using them, and that way keep them straight. So that's where this little convention comes from. Okay, so we've allocated, we've filled the arrays. We're going to allocate our device arrays. We don't fill them with anything at first, they're just there. Then we're going to fill them from the host arrays. So I fill array A on the device with from array A on the host, size, number of integers, and host to device. Repeat that for device array B. Here we call our kernel. So I've got the vec_add kernel, 1 block of threads, 32 threads per block. And then we've got a kernel parameters. We're going to add together DA and DB, save it in DC, and they're all of length size. Quick note here, I did use 32 threads, and I only have 16 elements. But because we've got this guard here, we know we have 16 elements, and we're not going to let those other 16 threads do anything. So they're sitting idle, but I just went ahead and gave it an allocation of 32 threads, basically just to show that point. But the greater point here is generally you want to write your kernels in such a way that you can have extra threads and it not try to access memory that's not valid or do things that aren't allowed. But anyway, we run our kernel. When that's done, we copy back. We fill the output array HC with the device output array, and then we print it out. We free those, and I almost forgot, we've got to free these as well. Oops, that's not what I meant to do. Okay, so that's our program. Now to run it, first I'm going to log into Firefly. So I am logged into Global Protect here. You got to have this set up in order to get in. You got to be able to get into the VPN in one way or another. This is just how I do it. From there, SSH your username at firefly.simcenter.utc.edu. Just going to ask for my password. Okay. And then you pick the node that you want to run on. I'm going to choose 02 because it's usually empty. All right. We're going to module load CUDA 10.2. All right. It's important that you use 10.2 on Firefly. If you use just module load CUDA, you'll get a newer version than it's ready for and it breaks things. So make sure you have 10.2. This program happens to be located in this location. And then, so the first, breaking down the command, NVCC is just the compiler name. That first file path is the path to the input file that I want to compile. -O says output the result of the compilation to this place, which I'm going to call that. Okay. And then to run it, we just type the name or path, I guess, of the compiled file. And you can see it prints out 2 through 32, all evens, and that's because we added 1 through 16 to each other. So this is all the doubles here. So that's good. We compiled without issues and ran. We were able to see our results, and that's basically it. At this point, you should be pretty much prepared to run some basic CUDA programs. that is just about everything I've got. So any questions on any part of it? Okay. All right. In that case, the only thing left is to give you guys homework. I'm not going to do any real homework. I'm not going to grade anything or nothing like that because I can't grade anything. This is just an informal class. But it is very important that you guys get hands-on. So I think what you should do and what I would like you to do is come up with some really simple kernel. It can just be like, I don't know, double the contents of an array and save it to another one, or multiply two arrays together instead of adding them, or something. And go through the steps yourself, make a new program, don't copy mine, and build it piece by piece. I recommend you compile often. That way you catch things as you go. And that way you get a feel for building it up until it's ready to run. Because it's got a lot of components. There's a lot of things here. I know some of you have used CUDA before, but still, I would recommend just make sure you got a handle on this by just making some sort of basic CUDA program. This and other examples are in the Learn CUDA repository that I shared with you guys. And of course, you can always just send me a message. I made a Slack channel for this class, so feel free to post questions there, and I'll answer them there. That way, everyone can see them. I guess that's it. So I'll ask one last time. Anybody have questions about the class itself, what I'm asking you to do, anything I covered today, anything else? Okay. In that case, you are all free to go then, and I'll see you guys next Friday. Oh, do you have something, Evelyn?
Yeah.
Okay.
Is there any like site you can recommend for like if a person has some free time to go through some examples or something?
Yeah. So I actually wrote a whole series for learning CUDA, and it is online. I actually sent it to you guys in your first email, but I can put it back on the Slack channel.
It's
there's
okay
the
if you say it, I'll go and check it.
Okay, well, it's if you wanted to find it, I think it's github.com/rshipley160/learnCUDA. That's a lot to remember. So
Oh yes.
yeah. So yeah, it's on GitHub. I'll get you guys the link to it.
Okay. Thank you. Thank you for the lecture.
Welcome. Imagine that doesn't happen to a whole lot of lecturers getting thanked for it. But thank you. I appreciate it. Appreciate it. Okay.
Yeah.
Thank you.
Welcome. Welcome. All right. If nothing else, I will end the meeting, and you guys are free to go about your day. You guys have a good weekend.
Thanks, you too.
Bye, you too.
All right. Bye, everyone.